All right, so let's do it. We're going to start in on our next chapter here. Our focus is going to be on electrochemistry, which just sounds cool, all right? It's actually a pretty important topic in modern day chemistry because, as everybody knows, we're really trying as a species to break our addiction for fossil fuels. Dr. Yang talked about this at the beginning of her video as well. One of the problems, there's two main problems here. Number one, fossil fuels are an amazing source of energy. I mean, it just turns out that breaking those carbon-hydrogen bonds releases a crap ton of energy. Like per gram, there's not much of a better fuel out there. So that's one problem. The other problem is we actually have some means of generating energy based on, this big, huge star that we got burning a few, however many miles away. I have no idea. Should probably put a number on it. Anyway, releasing a crap ton of energy, right? And we finally figured out how to harness some of that. We have these winds blowing as well. We can harness that energy. We've managed to get that far. The big problem is that energy is intermittent, right? Meaning it's not all the time. The sun doesn't shine all the time. The wind doesn't blow all the time. So if we're going to take those as our energy source, one big challenge is storing that energy in batteries. And so battery chemistry has become a very popular topic. Electrochemistry is exactly that, the chemistry that occurs within a battery. Okay? And electrochemistry focuses on a specific type of chemical reaction, what's called an oxidation reduction reaction, otherwise simply referred to as a redox reaction. All right, and this is a particular class of chemical reactions where electrons are exchanged between elements. All right, this is not the case for all chemical reactions. All chemical reactions involve electrons in the sense that reactions are about making and breaking bonds, and bonds are made up of electrons, but usually we don't change who's associated with those electrons, right? They bond to different people, but it's not like we pull an electron off of one element and give it to another, all right? That's not the case with every chemical reaction, but that's exactly what we see here for these redox reactions. We're actually going to take an electron from one species and give it to another. There's this transfer of electrons that's occurring in a redox reaction. Because of that, they're kind of a pain in the butt, a little bit more complicated than reactions that we've seen before when it comes to balancing those chemical equations. And so that's what we're going to focus on here first. So let me give you an example of a redox reaction. Turns out that if you take solid iron and you toss it into a solution of zinc ions, you will get solid zinc metal and iron 3 ions. All right, so if we look carefully at what's happening here, we see that my iron is going from being solid, neutral iron atom to now having a charge of +3. All right, so it goes from being neutral to being an ion. All right, from not having a charge to having a charge. And likewise, our zinc does the exact opposite. It goes from being an ion to being an atom. It goes from having this net charge to now being neutral. Okay? So let's think about this for a second. In order to go from being a neutral atom like iron to being an iron 3 ion, is it going to be gaining or losing electrons to get that positive charge? It's got to get rid of them, right? Electrons are negatively charged, so my iron is losing electrons. right? But electrons are particles. They're not just going to disappear into thin air. We can't be destroying matter here, right? So what's happening to those electrons? Our other species here, our zinc, is then gaining electrons, which is how it goes from being the zinc ion to neutral zinc here. Okay? So again, a redox reaction. We have this exchange of electrons that's occurring. And we have fancy names. The thing that's losing electrons, we call that oxidation. Gaining electrons, we call reduction. Hence the name, oxidation-reduction reactions. Okay? Part of what you're going to be doing when you're balancing these chemical equations is telling me who's being oxidized and who's being reduced. So if you're losing electrons, you're being oxidized. They have a little acronym to help us remember this. LEO, losing electrons, is oxidation. Okay? The other way that you can kind of look at this and get that same sort of thing is the element that's being reduced is going to go down in charge. And that makes sense because reduced means go down. So you're looking at who's decreasing in charge. That will tell you which element is being reduced. There is always going to be one thing being oxidized and another thing being reduced. You can't have oxidation all by itself. You can't have reduction all by itself. All right? Because again, we have an exchange of electrons. Something's going to be losing those electrons. Where do those electrons go? To the thing that's gaining those electrons. Okay? Now, I said that these reactions are going to be kind of because of this transfer of electrons, they can be kind of a pain in the butt to balance. Up until this point, every chemical reaction that you've been balancing, you've been doing what's called mass balancing, where you look and make sure that you have the same number of chlorines on one side as you do on the other side. Same number of hydrogens on one side as you do on the other side, right? That's what we do when we balance chemical equations. If I look at this chemical equation is indeed mass balanced. I got the same number of irons on both sides. I got the same number of zincs on both sides. Okay? So what's the problem here? Well, my iron, how many electrons is it going to have to lose to become the iron 3 ion? It's got to get rid of 3 of them, right? So it's going to lose these 3 electrons. Zinc, going from being zinc 2 to neutral zinc, gains how many electrons? 2. So where the heck did that extra electron go? Okay? The problem is that our reaction isn't balanced yet. We got to account for those electrons when we balance these reactions. We have to do something we call charge balancing. So what I'm going to do to charge balance, to sort of see how to balance this here, is we're going to break this up into these 2 reactions. I'm going to look only at the oxidation reaction, right? What we would call the oxidation half reaction here, where I have iron going to the iron 3 ion. And then I'm going to look at my reduction half reaction, where we have a zinc ion going to being neutral zinc. All right. Down here. So now we're going to take these 2 half reactions here and we're going to add electrons to charge balance. And what I mean by that is the same net charge on both sides of your chemical equation. All right, so what the heck do I mean by this? Let's look at our oxidation half reaction first. I'm gonna figure out what the net charge is on my reactant side here. I have this neutral iron atom. So what's the net charge if it's neutral? Just 0. And if I look on my product side here, I have this iron 3 ion, right? So what's the net charge on my product side? Plus 3. So my half reactions are not charge balanced. I have a different charge on one side than I do on the other. And how we're going to correct this is by adding electrons, all right, to our chemical equation here. What is the net charge of an electron? Positive or negative? Negative. So the only thing I can do is add negative charge here, okay? So in order to charge balance, and again, this is our net charge down here, I'm going to add 3 electrons to my product side, because now if I sum everything up, my net charge is 0. All right, so then I want y'all to take a second and see if you can balance our reduction half reaction here. All right, charge balance that reduction half reaction. As is, my reactant side has a net charge of +2, and my product side a net charge of 0. I can only add electrons, right? So in order to balance this out, I'm going to add 2 electrons to the reactant side of my reduction half reaction. So now if I sum all this up, I get that net charge of 0. All right? And this will be something that you see all the time. I'm going to, again, ask you what's being oxidized and what's being reduced. Remember, oxidation is losing electrons. And so as you can see, the electrons appear on the product side. Reduction was gaining electrons. And so you can see those electrons are on the reactant side of our balanced half reactions here. Okay, and just to be clear, in this particular example, both of these, when I did my charge balancing, they worked out to be 0. That's not always going to be the case. The bottom line is you need the charges on both sides to match. They don't both have to be 0, they just both have to be the same value. All right, so now I need to combine these back again. Okay, so now we're going to combine these half reactions. But we're going to do so in such a way that our electrons cancel out. All right, so what do I mean by that? I'm going to take these 2 half reactions that we charge balanced. So here was my oxidation half. Here's my reduction half. All right, I'm going to sum these up, add these back together. But I need to do so in such a way that I can cancel out my electrons. Currently, if I summed them up, I would end up having 1 extra electron on the product side. They're not going to cancel out, right? So I need to sum these up in such a way that everything cancels out. But I can't just change the number of electrons that I have over here to 2, or it won't be charge balanced anymore. So how do I keep these things charge balanced but still cancel out my electrons? I'm going to have to take these whole half reactions and multiply them by a particular coefficient. All right? There's no way to turn a 2 into a 3 or a 3 into a 2. So I got to turn them both into their least common multiple, which would be 6. So I'm going to take this entire half reaction here and multiply it by 2. And I'm going to take this entire half reaction down here and multiply it by 3. That way I have 6 electrons on my reactant side, and I'll have 6 on my product side. Importantly, that multiplication factor will hit everything inside those parentheses. So now I also have 2 iron ions and 3 zinc ions. I'm sorry, iron atoms and 3 zinc ions. That'll give me 2 iron ions, 3 zinc atoms, and again, 6 electrons. All right, so again, I need to combine these half reactions in such a way that our electrons cancel. I don't want to unbalance my half reactions. I just went through all that trouble to balance those half reactions. So what I can do that's going to keep them all balanced but make it so that I can cancel out my electrons is to multiply the entire half reaction by a certain value that'll make it equal to one another, right? So now I have 6 electrons on both sides, which allows me to cancel those out. And so my overall balanced redox reaction here is my 2 irons plus my 3 zinc ions gives me 2 iron ions and 3 zinc atoms. All right, and this was not a conclusion that you could have arrived at just by mass balancing this chemical equation. You have to look at the electrons here. We have to charge balance these redox reactions. All right, so we're going to complicate things a little bit. Let's look at another redox reaction here. These redox reactions typically take place in aqueous solution, and because of that, there's a whole lot of what floating around? Water. All right, and so oftentimes water is actually participating in these chemical reactions as well. When we write our chemical reaction for our redox reaction, let me give you an example here. Iron 2 plus permanganate this takes us to iron 3 and a manganese ion. All right, so take a second to copy this down. All right, so again, our goal is to balance this chemical equation here, this redox reaction, and now we see we have another complication. we have this permanganate ion with oxygen on the left-hand side, and there is not oxygen that appears anywhere on the right-hand side, right? So there's this sort of built-in assumption that water is involved in these reactions, and so when we balance that, we have to account for that, all right? So we're going to learn this method for balancing these reactions. It's going to sort of piggyback on what we just did before, okay? It's going to be a step-by-step process here. Step one. We're going to break into our half reactions. All right, so I need to look at what's happening to this iron ion all by itself. So it goes from being iron 2 being iron 3. All right, is it gaining an electron or losing an electron? Is this oxidation or reduction that we see here? So this one would be oxidation. All right, so for our other half reaction, I'm going to take my manganese, rather my permanganate, and my manganese ion. Okay, now because of that oxygen, it's a little harder to see what's going on here, oxidation or reduction, but again, if something's being oxidized, the other thing must be being reduced here, all right? And we could also figure this out after we charge balance. Like I said, you'll always have electrons as a product for your oxidation half reaction, and we should see electrons as a reactant for our reduction half reaction. So step one is to break into these half reactions here. All right, step two is we're going to mass balance everything except oxygens and hydrogens. We got to save those for later. We got a special way to balance our oxygens and our hydrogens in this reaction. So I'm going to look at my oxidation reaction. I'm going to ignore oxygens and hydrogens. There aren't any anyway. And I'm going to mass balance this half reaction so that I have the same number of irons on both sides. Do I have to do anything, or is it already mass balanced? I'm good here, right? There's one iron on both sides, okay? If there was any sort of a mix, if this is Fe2, which doesn't even exist, but if it was, you'd have to mass balance. Okay, same thing over here for this particular example. My manganeses, I have one on the left and one on the right. Again, I'm ignoring oxygen at this step, so check, check. These are mass balanced with everything except oxygen and hydrogen. All right, so now I got to deal with these oxygens here. So now what we're going to do is we're going to balance the oxygens by adding water. Again, there's just kind of this implicit assumption that water is involved in these reactions. Okay, my oxidation half reaction. I don't have any oxygens. I don't have to worry about that. But if I go to my reduction half reaction, I have this imbalance because I have oxygens on the left-hand side, but none on the right-hand side. Okay, so I'm going to balance these by adding water. And since I have them on the left but not on the right, I'm going to add my water on the product side. How many waters am I going to add to balance those? 4? All right. Well, now it just seems like we took another step back here. Now I got hydrogens on one side but not on the other side, right? So how do we deal with that? Again, this is a reaction that takes place in an aqueous solution that is acidic. So the other implicit assumption here is that these hydrogen ions are involved in our reaction. So now we're going to balance the H's by adding hydrogen ions, by adding protons, H+. Again, don't have to worry about it for my oxidation half reaction. There's no oxygens or hydrogens. But in my reduction half reaction, everybody take a second and balance the hydrogens by adding hydrogen ions. I'm going to need to add 8 hydrogen ions to the reactant side of that reduction half reaction in order to balance everything. All right, so now if I go through and count atoms, everything is mass balanced in both of these half reactions. So now I'm ready to include that step that we discussed. I'm going to charge balance these half reactions. And again, we do that by adding electrons. Everybody take a second and see if you can't charge balance these two half reactions. So in order to charge balance my oxidation half reaction, I got to add 1 electron to my product side so that the net charge on both sides is +2. My reduction half reaction is a little trickier. All right, I have 8 hydrogen ions. Each one has a charge of +1. So if I got 8 of them, what's the total amount of positive charge there? Yeah, and then accounting for this negative charge right here, that gets me to +7. Over here I have 1 manganese ion and 4 neutral waters. Those waters aren't going to account to my charge. So my net charge over here is +2. So how am I going to make these equal to one another by adding electrons? I'm going to have to add 5 to the reactant side of my reduction half reaction. Again, you can only add electrons, so you can really only bring a number down. You can't make it go up, right? So I have a bigger number over here. If I then add these 5 electrons, now all of a sudden my net charge is +2, so they match. All right, so then the last step here, now that we got these things finally charged, balanced, we can combine to cancel those electrons. So everybody take a second and see if you can't give me my balanced chemical equation for this reaction here. All right, we got to combine these, but do so in such a way that our electrons will cancel out. right, so if I add these up as it is, I'm not going to cancel out my electrons. I also can't just make this like a 5 here arbitrarily, because then that throws off my charge balance of that half reaction. So the only thing I can do that won't mess it up is to take this entire half reaction and multiply it by 5. That way I have 5 electrons on my reactant side. And remember that 5 will also hit everything in those parentheses. So now I have 5 iron 2s. And importantly, now I have 5 electrons on my product side as well. So I get to cancel those out. All right, and I'm left with now my balanced chemical equation for this redox reaction. Right, so we got this kind of pain in the butt process for balancing these redox reactions here. And it all revolves around the fact that we got to charge balance these reactions. Okay? If our redox reaction takes place under acidic conditions, we got to follow these steps. We got to break it into the half reactions. All right? If they contain oxygens and hydrogens that aren't balanced, we have a way to deal with that. First, we're going to mass balance everything except those oxygens and hydrogens. Then we're going to go through and balance our oxygens by adding water. And since this reaction takes place under acidic conditions, we're going to balance our hydrogens with hydrogen ions. Once we've done all that, then everything's mass balanced, and we can charge balance by adding electrons and then stick it all back together again. All right, cool. And so yes, when we get finished here, we can see that because it's under acidic condition, we have these hydrogen ions and we have these waters that appear in our chemical equation once everything's all nice and balanced. All right, let's do another one. Iodide ion, and again that permanganate. These will react to form iodine. And manganese 4 oxide. We're going to do another redox reaction balancing, but this time this reaction takes place under basic conditions. All right, but everything kind of starts out the same. We're going to have to tweak this just ever so slightly. All right, but you're going to follow these same steps that we laid out before, so let me just copy and paste them over. Okay, I want everybody to take a second and see if you can't do these first 4 steps on your own here. I'm going to give you a few minutes and then I'll go in and walk through. right, and to be clear, yes, I'm going to ask you what is being oxidized and what is being reduced, but honestly, you can wait until you get to the charge balancing step and see where you put your electrons to label them. All right, the important stuff is that you break it up. So here are two half reactions. I want to warn you that last time we didn't have to do anything for step 2 here. That is not the case for these reactions. They are currently not mass balanced, everything except hydrogen and oxygen. So look carefully and make sure to not skip that second step. So if I mass balance my half reactions, importantly for this half reaction here, these iodines are not balanced. I have to stick a 2 out front of my iodide ion in order to balance this half reaction. My other half reaction, my manganeses, are balanced. Now I'm going to go through and balance oxygens by adding water. I don't have to worry about that for my iodine half reaction, but my manganese half reaction is unbalanced. So I'm going to add 2 waters to balance this out. So I have a total of 4 oxygens on both sides. Let me make some room. All right, so now I got everything that isn't oxygen and hydrogen and oxygen balanced. So now lastly, I'm going to balance my H's by adding H+. So that's a total of 4 over here. Cool, so if this was acidic conditions, I would then charge balance and be done, right? Combine everything. But these are basic conditions here. That's the whole shtick, is this reaction needs to be balanced under basic conditions. And under basic conditions, these hydrogen ions will not survive, right? They react to form water with, what ion do we associate with basic conditions? OH, right? So OH, if we got hydroxide in there, there's no way this thing is going to survive. It's immediately going to react, all right? So what we're going to do now, this special step that's just for basic conditions. Okay, special step. For basic conditions. All right, we're going to add hydroxide, and we're trying to cancel out those hydrogen ions. But if we add it to just one side, we're going to throw off the balance of everything. So what we're going to do is we're going to add hydroxides to both sides to cancel out the H pluses. All right, by adding it to both sides, we don't ruin our balancing that we just went through and did. Okay, I don't have to worry about it for this half reaction with my iodine, so let's just focus on this one here. Again, my goal is to cancel out these 4 protons here. So I'm going to add 4 hydroxide ions over here. But again, I don't just want to add it to one side, I want to add it to both sides, so I'm going to add the same number to my product side as well. That just keeps everything balanced. All right, so we added, because we're under basic conditions, we added hydroxide to cancel out those hydrogen ions. And now we can simplify. What's going to happen when 4 hydroxides combine with 4 protons? What are they going to make? Water. So these two together will combine to make 4 waters. All right, and we have waters on both sides. We can cancel. We can also wait till the end to do that. We're going to have to go through and do some canceling when we sum these up. So it doesn't really matter if you wanted to do it now or later. But the bottom line is now that we've added those OHs, we're back to our regularly scheduled programming here where we're going to charge balance and then finally combine. All right, so everybody take a second and see if you can't finish this off here. What's up?
Would you cancel the H2s on both sides? And if you do that before you add the coefficient outside the?
It doesn't matter. You could simplify it now, or you could simplify it at the end when you combine everything, and you would get the exact same result. Yeah. All right, so for this one, my net charge is -2 on the left-hand side, right? Because I have 2 of those iodide ions. And on the right-hand side, it's neutral. The only thing I can do is add electrons, so I'm going to have to add 2 electrons to my product side here. All right, and if I look at my second half reaction, water is neutral, so my net charge over here is -1. Over here, the only thing that's charged is those hydroxides, so my net charge is -4. So to make these things equal, I'm going to add 3 electrons to my reactant side here. All right? And look, right now is where we want to sort of do like a sanity check here. If you added electrons to the reactant side of both of these half reactions, something went wrong, right? You're always going to have one thing gaining electrons and one thing losing electrons. So I have to add electrons to the reactant side of one and the product side of the other, all right? So just an easy check if we maybe made a mistake along the way. We want to stop and review here, all right? The other thing I can do now, maybe a little bit easier than being able to see it before, is figure out what's being oxidized and what's being reduced. For the iodine, my electrons are on the product side, so which half reaction is that? Oxidation is losing electrons, so they're on the product side. For my other half reaction, the electrons are on the reactant side, so that's our reduction half reaction. All right? So sometimes it's easy to tell, especially if there's not any hydrogens or oxygens involved. Otherwise, it's just easier to go through and charge balance it, figure out where you put those electrons. All right, and so then our last step here, now that I have this all charge balanced, is to combine these. So let's put our oxidation half reaction. Oops. All right, just to get rid of some of this crap here, I'm going to get rid of these waters now. Cut that down to 2. And so I have 3 electrons on my reactant side and 2 on my product side. Those obviously aren't going to cancel out. You can't make a 2 into a 3, but what we can do is turn them both into their least common multiple. So I'm going to multiply this side by 3, so I have 6 electrons, and multiply this one by 2, so I have 6 electrons, and then I can combine it all together. Right, and remember that coefficient is going to hit everything inside those parentheses. So now I have 4 waters and 2 permanganates and 6 iodide ions. All right, and the whole logic is if I did it right, my electrons cancel out, and I'm left with my balanced chemical equation for my redox reaction. All right, kind of a pain in the butt. Not something that you can just do by looking at it. Like we kind of got good at balancing other chemical reactions where we kind of just could look and see what needed to happen. Not going to work like that, right? Make sure we follow our step-by-step procedures here. Okay, cool. All right, we'll pick up with this on whatever the next day is. Friday. Oh, snap. That's awesome. Cool.